And could you make it in 5 minutes?
5 minutes?
Yes, I know, you have to run a little bit, but we have the coffee break.
What was that?
But try to do your best.
Yes, I'll try to do your best. But I think I have to talk about Hassan because for me it was I can't. Ah, yes. Okay. Can you hear me?
A little bit closer.
Okay. He was a sort of father. I think I met him, father scientifically, of course. I met him when I was doing my thesis, and at that time, I have to say, not many people were having this double crossing interest between different areas like Hassan. And I think his papers were very an inspiration, and also as a person, because first of all, his papers were extremely well written. That I cannot say is is very common nowadays. And because I think that really he was a passionate person. So he was doing what he was doing because he really liked it. And I think he was supporting young research very much. Like me, I was not his student, but he was always encouraging. So I have to say something like this. And in particular, it's through her son that I started learning this crossing between fluid mechanics and celestial mechanics. That is also something that was very powerful. So my work nowadays is between Carlissimo, there is another very inspirational figure, and Jerry Kohler. And just the bottom line of what I do with them, and I can explain you more about in private. Just this, with Carlissimo, I say we can do arts. Because this figure, that of course you don't understand what it is just related to existence of rings, of vortex ring on a sphere, but not identical ring, different rings. So according to the situation, we have more curve. More curve means possibility of different kind of equilibria. And in particular, the Z1 and Z2 are referred to the vertical position of the first ring and the second ring. So according to the vorticity, we have different kind of scenario. You cannot place your ring wherever you want. So this is strongly related to the vorticity. So we have some analytical result about that. And then instead with Jair Kohler, we are interested in how vortex dynamics, how does it change from surfaces that are deformed from the sphere. So I take a sphere, I deform conformally. What kind of point vortex dynamics, what kind of eventually fluid dynamics I recover. So in particular, you take a sphere, you take one vortex, the vortex is not moving. Now we can prove that I deform the sphere and this vortex is start moving. And this is produced by the reaction of the vortex with the geometry, and in particular the variation of geodesic curvature. But okay. But since I'm here, that's it for my work. I want to spend a word about why RF is so much interested in relative equilibria. And I think that somehow Cambridge is a good place for it. Because, I mean, if Descartes start talking about vortices to explain the solar system, the stability of the solar system, was Newton that came out with the idea that, you know, the proof that actually vortices were not exactly appropriate because of vorticity reasoning. But so vortices start to, we hear about vortices already in the 17th century, and Lord Kelvin, also known as William Thomson, has the vortex model. And J.J. Thomson, that understood he was a fellow, he wasn't a fellow at the Trinity College, I think, no? Was it? He starts studying relative equilibrium configuration. Why? Because he thought this was one of the first, at that point, was a model for the atom. I mean, they didn't know any better than that the Coulomb interaction, and so they thought that the electron has to distribute in some polygonal configuration. So actually, Thomson has studied linear stability of this configuration. And in fact, there is a very nice book, Electricity of Matter, that here you see like a fellow of Trinity College. And in this, they start doing experiment, and what you see, relative equilibrium configuration of vortices, of concentric vortices. These experiments were actually done with floating magnets, and I don't know if these experiments were done on the Cam River or not. This I don't know, but they were the way at the time to test the Thomson, J.J. Thomson prediction. And of course, we already know that the equivalent we heard already by Morten, that about vortex line, the extension of point vortices, and we've seen also that actually polygonal configuration appear in the case of magnetic field lines. But also want to say that polygonal configuration also we find in fluids in the atmosphere. So for example, this is the Earth atmosphere, and this situation actually appears when the southern polar vortex is active. And so you see that this is a jet, it's a polygonal jet, that this was in 98, that persisted for quite a while. 4 days is quite a time. And so this kind of situation are possible when the polar vortex is there, and so the polar vortex allows and stabilizes this kind of configuration. You see also on Saturn, you see similar kind of polygonal configuration. So this is why, if you want to extend the work of J.J. Thomson on the sphere, what about polygonal rings of vortices on the sphere? And so this is what we've been doing. And the other point I want to make, that when you do vortex dynamics, I'm just skipping, it's crucial to solve the Green function. And the Green function, for example, for the planar case, enter, for example, in the Hamiltonian of two vortices, and enter in the Hamiltonian of n vortices, like we've seen in the talk by Morten. But this is only for surfaces that are constant in curvature and not boundary. When you consider boundary, you have to add an extra term. It's our friend, the Robin function. And I will be happy to talk about you. And for example, it's clear some situation are intuitively clear. If I put one point vortex in a plane with a boundary, it doesn't move. But if there is a boundary, now the vortex are moving. And the same thing happen here. As I say, if I have a surface with a constant curvature like a sphere, it doesn't move. I deform a sphere, it starts moving. And we have a geometrical way to deduce this Robin function in this case, and how this link to variation Gaussian curvature. So I think this is it.
You have a poster on that?
No, but I can talk to you about
papers. Typical.
It's a virtual poster.
Then maybe we all go to coffee, and I thank everyone.